Related rates problems are probably one of the hardest kinds of problems in calculus. At least I always thought so when I was learning it. It took me quite a bit of practice to get those down, so I wanted to show you the 4 easy steps that you can do for any related rates problem so that you can solve these much more easily and learn this process a lot quicker. And this problem is actually one of the ones that I did in last week's live stream. I'm doing a weekly live stream now every Monday night at 5 Pacific, 8 Eastern. Be sure to join us. You can come and get your questions answered and go over some calculus topics live. But without further ado, let's go ahead and jump on into this example. The problem we're going to do is we're going to have the altitude of a triangle is increasing at a rate of 1 centimeter per minute, while the area of the triangle is increasing at a rate of 2 centimeters squared per minute. At what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 100 centimeters squared? So I think, when I first read this problem, first thing to kind of point out is altitude is a little bit of a, not super common terminology you see with triangles, but basically just treat that as the height of the triangle. So the first thing you want to do with these related rates problems is always going to be to draw a picture of what you're dealing with. There's generally 4 pretty simple steps that you're going to go through for all related rates problems. They'll pretty much get you to the answer every time. And the first is always going to be to draw a picture, because drawing a picture is really going to help make it a lot easier for you when we get on to the next steps and kind of figuring out what equations we're going to need to be working with. So obviously we have this triangle with the altitude of the triangle, so the height of the triangle, increasing at a rate of 1 centimeter per minute. So basically we know that it's growing at a rate of 1 centimeter per minute. We also know the area of the triangle is increasing at a rate of 2 centimeters squared per minute. So basically I'll just kind of draw that in here, 2 centimeters squared per minute. Okay. And then we're trying to find the rate that the base of the triangle is changing when the altitude is 10 and the area is 100. So one really important piece of doing your drawing is to kind of label different pieces in your drawing with a variable. So what we want to do is, in order to figure out what pieces we actually want to label, because you don't want to just go labeling everything all willy-nilly and just throw all these letters all around your drawing, because that's really just going to make things more confusing than it needs to be. What we really want to do is think about which measurements are actually going to come into play here. So the first thing that you want to do when you're kind of doing that is think about what is the measurement that the question's actually asking us to figure something out about. And in this case, it asks, what rate is the base of the triangle changing? So we know that we're going to try and figure out something about how fast this length right here is changing. So we know that we're probably going to want to label this side at some point. So I'll just go ahead and call this y. And since it's asking for the rate that this is changing, basically we know that what we're trying to find in the end is dy dt, which is how fast y is changing with respect to time. So this is our final goal here, is to find dy dt, given that we're labeling our base as y. The other thing we want to think about is what pieces of this triangle, or what measurements in our drawing, has the question actually given us some information about. So we have been given information about this height, or this altitude. We've also been given information about the area, right? We have not been given any information about the hypotenuse. So we're probably not going to consider that as one of the sides that we want to label here. We want to label our altitude, or our height, and we want to label our area, because those are the things that we actually have some information about. And in fact, in this kind of final piece here where it asks us to find dy dt, it also gives us some more information, not only about how quickly these things are changing, but what their measurements are at the specific instant that we actually care about also. So we also know that the altitude is 10 centimeters and the area is 100. So since we know their actual measurements, the altitude and the area, and we know about how fast those two things are changing, those are probably going to be the other 2 things that we want to label. So we'll go ahead and just call the area capital A, and we'll call the altitude, or the height of this triangle, x. So the kind of moment, or the instantaneous, spot in this triangle's growth or change in shape and all that we actually care about is going to be when our altitude is 10 centimeters. So when x is 10 centimeters, and when our area is 100 centimeters squared. So when our area is 100 centimeters squared. The units you really don't have to worry about too much when you're going through these problems. Technically that probably would be correct to label your units and use those in the equations, but as long as you're setting up your equation in a way that geometrically actually makes sense, those units are just going to end up canceling out and getting you to the answer that you would expect based on the units that you've been given in your answer. So I'll touch on that a bit more. That'll probably make more sense when we get to the end, but I'm not going to worry too much about the units as we work through this problem. Once we have gotten our drawing and once we have labeled everything in our drawing that we're actually going to need to use, the next thing we need to do, the next step of these related rates problems, is going to be to come up with your equation that basically relates different measurements in your drawing or different measurements in the scenario that's being described. So in this case, we want to think about what kind of equation we can come up with that's going to relate the area of our triangle with the height and the base. Well, probably the best place to start, and of course, sometimes this takes a little bit of guess and check. You need to kind of come up with an equation, see how well it works, and if it doesn't work, come up with a new equation. But in this case, since we have area, base, and height, probably the best place to start would just be with the equation for the area of a triangle, which is that the area of a triangle is just 1/2 times the base times the height, which in this case is going to be x and y. So then once you've come up with your equation, what you want to do is you're going to take the derivative of both sides of your equation using implicit differentiation, and we're going to take the derivative with respect to time. It is possible that you may take the derivative with respect to something else, but I'd say like 99% of the time or more, you're going to take the derivative with respect to time, because these related rates problems, they're always going to be asking how quickly or what rate some measurement is changing, which basically what that kind of implies is that we are trying to think about how it's changing with respect to time. So you're generally going to take d dt of both sides of your equation. So this is, like I said, the implicit differentiation step, because we have these other letters here, a, y, and x, that we know are not the variable, right? Going back to the implicit differentiation problem we just did, we know because we have this t down here on the bottom that t is the variable. A, y, and x are actually functions of t, functions of time. So when we're taking the derivative of a, y, and x, we don't actually know the derivative of a, y, and x. So just kind of starting with the left side here to take the derivative of a with respect to t, since we don't know a, really, I mean, we know what a is in relation to x and y, but we don't know what a is in relation to t, which is our variable. What we want to do is just take the derivative with respect to time. Well, the best we can do really is to say that the derivative of a with respect to time is just going to be dA dt, because that literally just means the derivative of a with respect to t. So now to take the derivative of the right side of our equation, you can see again, kind of like our last example, we're going to have product rule here because we have y times x, which are two separate functions. So when we're taking the derivative of 1/2 times y times x with respect to time, we have the product of these two functions here. So what we can do is just kind of keep this 1/2 out here, out front, and take the derivative of y times x and then multiply 1/2 times that whole derivative. So to do that, I'll again kind of do a side problem of product rule over here. So again, we want to figure out an f and a g. And again, it doesn't matter which one we call which. So we can call f our y and g our x. And then we need to find the derivative of each of these. So the derivative of f, the derivative of y, with respect to t, is, again, just like we did with our a over here, it's just going to be dy dt. And then same idea here with g prime, the derivative of x with respect to t is just going to be dx dt. Okay, and now product rule again says that we're basically going to cross multiply these. So we're going to take f times g prime, g times f prime, and then add them together. So y times dx dt plus x times dy dt, and then we'll close our parentheses there. So now once we have done this, once we have taken the derivative of both sides of our equation with respect to t, done the implicit differentiation step. What we want to do at that point is to actually start plugging in some of the values we know. Now, you want to be careful. You never want to plug in values before the implicit differentiation step. If you do, you're going to eliminate answers and you're not going to get what you should be getting. So to do that, some of these things we already know. We were basically given that we're looking at the point in time where x is 10 and where a is 100. So we already know that, at least x we already know. We don't really have, we don't have all these is what I'm getting at. We do have the rate of change of a and the rate of change of x, which I did right over here in our drawing. dA dt is always just going to represent the rate of change of a, how quickly a is changing. Well, we were given that the area is increasing at a rate of 2 centimeters squared per minute. So we know that dA dt, the rate that a is changing, is just going to be 2. So we can plug that in for dA dt. We also know that x, the altitude of our triangle, is increasing at a rate of 1 centimeter per minute. So we know that the rate of change of x is 1, so dx dt is 1. We don't know why quite yet. We can figure that out though. So I'll actually come back to the dx dt in just a second. So first let's think about y here. If we look in our drawing, y wasn't given. We know the moment in time we're looking at is when x is 10 and when a is 100, but we weren't given what y is. It didn't tell us what the base of the triangle was at the moment we want to look at. However, we do know a relationship between a, y, and x. We know that a is always going to be 1/2 times y times x. So we know that a, 100, is always going to be 1/2 times y times x, which is 10. So we can kind of set up this relationship and solve for x. So 1/2 times 10 is 5. If we divide both sides by 5, that gives us y equals 20. So we actually do know y, even though it wasn't given, we were given the information that we need to figure out what y is. Okay, and then dx dt, like I said, is just 1. And then we have plus x, which we are given that we want to look at the moment when x is 10. So we're going to put in 10 for x. And then times dy dt. Well, remember, dy dt was the thing that we were looking for. That was our goal all along. So obviously we don't have that at this point. So now we have this equation, which we have plugged in all the information we know. And we have this, at this point, this equation, which only has dy dt, which is the thing that we're looking for, and then a bunch of other numbers. So now we have a single equation with a single variable. We should be able to just solve for the thing we're looking for, and that should be our answer. So we can just kind of simplify this. We will have, we can multiply both sides by 2 to cancel out the 1/2. So that'll give us 4 equals 20 times 1, which is just 20, plus 10 times dy dt. Then we can minus 20 from both sides, giving us negative 16 equals 10 dy dt. And then we can divide both sides by 10, which gives us dy dt equals negative 1.6. And now this is kind of what I was getting at earlier, where the units come into play. We are being asked to find at what rate the base of the triangle is changing. Well, since the base of the triangle is a unit of measurement that we would use centimeters to measure, the rate of change of centimeters is going to be centimeters per minute, because we know that these other rates of change were measured in minutes. So basically we know that it's going to be changing at a rate of centimeters per minute, just like this other side length was. So we can go ahead and say that it was changing at a rate of negative 1.6 centimeters per minute. So in other words, in order for the area to increase by only 2 square centimeters per minute, if this side is increasing at a rate of 1 centimeter per minute, this side would actually have to be shrinking because it has a negative rate of change at a rate of 1.6 centimeters per minute. If the question asked us how fast is the base of the triangle shrinking or getting smaller, we would then make this positive and just say 1.6 centimeters per minute. But since it just asked what rate is it changing, we would want to make sure to keep that negative on there. Well, I hope you found that video helpful. If you did, please be sure to hit that like button down below and subscribe while you're down there too. Be sure to hit that bell icon as well so you're notified of all my new videos, and including when I'm about to go live, which will be on Monday night at 5 Pacific, 8 Eastern. See you there. And if you do want to keep learning about related rates, I have made a few other videos about that topic. be sure to click on one of those videos over there and keep on learning.